안녕하십니까. 로데슈바르즈 코리아의 최지홍입니다. 오늘도 저희 로데슈바르즈 코리아에서 준비한 웨비나에 참석해 주신 여러분을 다시 한번 감사드립니다. 2월 마지막 주, 오늘 지금 저희 준비하고 있는 2월 마지막 주는 이동통신 관련해서는 정말 주목할 만한 행사가 전 세계적으로 있는 날이죠. 그래서 이번 주 지구 반대편, 정확히는 이제 북반구 반대편에서 MWC가 열리고 있는 이 2월 마지막 주, 저희도 이러한 트렌드에 맞춰서 오늘 저희 6G를 주제로 하는 내용으로 웨비나를 준비를 했습니다. 오늘 이 관련된 내용으로 여러분께 좀 더 자세하고 또 흥미로운 이야기들을 전해드리기 위해서 저희 로데슈바르즈 코리아의 기술지원팀에 근무하고 있는 유승근 매니저 자리에 함께 해주셨습니다. 유승근 매니저님 소개해 주시고 인사해 주시죠.
네. 안녕하십니까. 반갑습니다. 저는 로데슈바르즈 코리아 기술지원팀에서 근무하고 있는 유승근 매니저라고 합니다.
예, 저희 유승근 매니저님 어떤 분야 지원하시는지도 잠깐 설명을 좀 해주시면.
네네. 저는 로데슈바르즈 코리아에서 주로 6G를 포함해서 4G, 5G, 모바일 기지국 및 이 중계기, 이동통신 쪽을 주로 전담하고 있는 기술지원 팀 인력입니다. 그러면
단말뿐만이 아니라 이제 인프라스트럭처에 관련된 부분도 지금 기술 지원 업무로 지금 진행을 하고 계신다는 말씀이시겠네요.
네, 맞습니다.
예. 저희 오늘 준비된 주제는 6G입니다. 그래서 아마 여러분들 대기 화면에서 보셨을 것 같아요. 싱크6. 저희 로데 슈바르즈에서 저희가 6G에 대한 내용으로 저희가 준비하고 있는 어떤 슬로건이라고 해야 될 것 같은데요. 싱크6라고 하는 이 6G, 아마 여러분들 들어보신 분들도 굉장히 많으실 거예요. 서두에서 말씀드렸습니다만 이제 MWC에서도 지금 이 6G에 대한 내용을 포함을 해서 5G and Beyond라든지 이런 식으로 주제를 설정을 해서 이제 6G에 대한 이야기들을 굉장히 많이 하고 있습니다. 또 흔히 우리가 이제 여러 인터넷 매체라든지 이런 곳에서 들어보면 2030년에 상용화가 될 거다 이런 이야기를 통해서 지금 우리가 쓰고 있는 5G의 어떤 더 업데이트된 좀 더 진화된 이런 이동통신 기술로서 우리가 6G라고 하는 분야를 생각을 하게 되는데요. 유승근 매니저님, 그러면 우리 이 6G라고 하는 게 우리가 그냥 관념적으로만 생각했을 땐 이동통신의 어떤 또 다른 형태가 아닐까 싶은데 어떻게 좀 자세한 내용들을 좀 설명을 좀 부탁드릴 수 있을까요?
잘 알고 계신 것처럼 4G 때는 주로 이동통신에만 저희가 포커스를 맞춰서 진행을 했고요. 5G로 넘어가면서부터 모바일뿐만 아니라 우리 오토모티브 그리고 인더스트리 이쪽 영역까지 확장이 됐고 6G로 가면서 추가적으로 NTN 그리고 Sub-THz, JCAS 그리고 울트라 매시브 마이모, 새로운 어플리케이션, 새로운 리서치 영역에 대해서 많이 찾아가고 있습니다. 그래서 6G라는 개념은 이제 이동통신에 국한된 게 아니라 좀 더 넓은 확장된 범위까지 이제 같이 가져가려고 하는 부분이 조금 달라진 부분이라고 할 수 있겠습니다.
예, 지금 말씀 들으신 것처럼 LTE, 우리가 보통 4G라고 생각을 하고 있죠. 이 LTE에서 이제 어떤 데이터 통신에 대한 부분이 굉장히 확장이 됐었다면 5G에서는 이러한 영역들을 이제 아까 말씀하신 오토모티브, 보통 URLLC, 초저지연 무선 통신 이렇게 이야기를 하더라고요. URLLC라든지 혹은 이 매시브 마이모, 매시브 IoT, 사물 인터넷에 대한 부분이죠. 이런 부분들까지 포함을 하는 일상생활 전반에 관련된 내용으로 확장을 하게 되고 이러한 추세로 더 나아가서 6G는 정말 말 그대로 우리의 모든 생활에서 일상에서 접할 수 있는 어떤 통신의 영역을 담당해주는 이런 기술로 지금 디자인이 되고 있는 것 같습니다. 그러면은 지금 6G라고 하는 부분이 지금 아까 제가 말씀드린 것처럼 2030년을 타겟으로 하고 있단 말이죠. 맞습니다. 그러면 아마 지금쯤은 뭔가 연구개발에 대한 내용들이 진행이 되고 있는 게 아닐까 이렇게 생각이 되는데 혹시 이 자리에서 간단하게 어느 정도까지 진전이 되고 있는지 이런 부분 설명을 좀 해주실 수 있을까요?
6G 영역에서 이제 신규적으로 이제 나오는 기술 중에 하나가 이제 신규 주파수 그쪽 영역에 대해서는 최근에 FR3 영역이 이제 지정이 됐고요. 그리고 오늘 금일 주제와 맞는 AI ML 부분은 5G 쪽에 있는 릴리즈 18부터 처음으로 AI ML 기술, CSI-feedback, 포지셔닝, enhancement 등이 나오게 됐는데요. 실질적으로 릴리즈 18에서 언급은 됐지만 이 대부분의 연구 과제는 릴리즈 19, 다음 연도로 이제 넘어가서 이제 개발이 되고 있고요. 그 외에도 JCAS 부분도 실질적으로는 OFDM 베이스의 신호와 FMCW 베이스의 신호들을 각각 나눠서 생각했는데 이런 부분들을 어떻게 합칠까? 라는 부분까지도 지금 확장해서 연구하려고 하는 부분들이 있습니다. 하지만 아직까지 딱 픽스돼서 이게 6G다 라고 하는 부분은 없고, 이제 조금 더 이제 4G에서 5G 넘어갔을 때 4.5G 이렇게 부르는 것처럼 5.5G부터 저희가 접근을 하고 있는 추세라고 보시면 될 것 같습니다.
그 좀 전에 설명해 주시는 부분에 잠깐 나왔습니다만 이 AI라고 하는 부분들.
네.
이번에 MWC에서도 이제 주제가 제가 알기로는 이 이동통신 5G의 그 어떤 진화에 대한 부분을 이제 5G and Beyond라고 표현을 하고 있었고, 그 다음에 게임 체인저라고 하는 이름으로 해서 AI라든지 이런 부분을 언급을 했던 걸로 알고 있습니다. 그리고 오늘 아마 주제도 AI와 그 ML, 머신러닝이라고 하는 분야가 되는데, 왜냐하면 제가 생각하고 있는 6G는 사실 어떻게 보면 이제 이동통신의 어떤 한 진화 족보로서 생각을 하게 되는데, 이런 부분에서 이 AI나 머신러닝이 접목이 된 어떤 부분이 있을까요?
사실 여러분들이 알고 계신 것처럼 AI, ML에 대한 연구는 사실 실제적으로 지금은 챗GPT로 대두될 수 있는 라지 랭귀지 모델, 여기에 포커스가 맞춰져 있습니다. 그래서 이러한 부분들이 어떻게 이동통신, 우리가 통신하면서 접목이 될 수 있는 부분에 대해서는 저희가 계속적으로 연구가 되고 있고요. 금일 동영상 동영상 웨비나를 보시게 되면은 저희가 어떤 스텝으로 접근을 하고 있는지 좀 더 보실 수 있고요. 그리고 최지용 매니저님께서 앞에 언급 주신 것처럼 MWC 라는 검색어를 지금 네이버나 구글에 해보시면은 다 AI, ML에 어떻게 이동통신을 접목해 볼 수 있을지, 우리나라에 이제 대표되는 삼성, SKT, KT 등에서 어떻게 할지들을 조금씩 스텝 바이 스텝으로 나가는 길이라고 보시면 될 것 같아요. 그래서 오늘 웨비나를 보시고 나면은 좀 더 어떤 식으로 어프로치 하고 있는지 조금 도움이 되지 않을까 생각이 됩니다.
예, 저도 지금 사실 오늘 이 스튜디오에 오기 위해서 쭉 이동을 하면서 왜 이 AI라고 하는 부분이 왜 6G하고 연관이 될까? AI 하면 여러분들도 아마 비슷하실 것 같아요. 우리가 보통 생각하는 AI는 가장 먼저 생각하기로는 이제 그 챗GPT를 생각을
맞습니다.
하게 되는데, 이런 글을 잘 써주는 이런 AI가 왜 6G에 나올까? 이런 부분들을 좀 고민을 했던 것 같습니다. 그래서 아마 제 생각으로는 이런 부분들이 또 굳이 이런 생성형이 아니더라도 또 어떤 그 네트워크의 어떤 최적화라든지
네.
이런 부분에서 또 어떤 역할을 하게 되는 게 아닐까. 이런 부분도 생각을 해볼 수 있을 것 같습니다. 저희 오늘 준비한 내용은 아까 잠깐 저 유승근 매니저가 말씀드린 것처럼 저희 로데슈바르즈 본사에서 준비를 한 그 동영상을 중심으로 저희가 준비를 했습니다. 그래서 이 머신러닝과 AI에 대한 부분들을 과연 6G에서 우리가 어떻게 기대하고 있는지, 또 어떤 식으로 그 모습이 나타나게 될지 이런 부분에 대한 전망에 대한 이야기를 좀 더 여러분께 들려드릴 수 있을 것 같고요. 이런 부분들을 함께 보시면서 또 6G가 이제 앞으로 나올 어떤 모습으로 또 새롭게 나올 수 있을지 이런 부분들 한번 좀 상상을 해보시면 어떻게 좀 재밌게 들으실 수 있지 않을까,
네,
이런 생각들을 해봤습니다. 예, 그러면 지금부터 저희 준비된 동영상 보면서 여러분들 함께 내용들 봐주시고요. 또 중간중간에 궁금하신 부분들 지금 채팅창으로 지금 인사해 주시고 좀 굉장히 활발하게 여러분들 활동해 주시고 계시는데요. 그 질문들 올려주시면 동영상 정리 후에 또 여러분들께 저희가 답변 드릴 수 있는 내용들도 정리를 해서 말씀을 드릴 수 있을 것 같습니다. 그러면 지금부터 저희 준비된 동영상들 함께 보시겠습니다.
Artificial intelligence is one, if not the buzzword of our time, but it's been around for 65 years. If I had to describe it in a few words, I would say that AI is a branch of computer science to engineer intelligent machines that mimic cognitive functions similar to the human behavior. It mimics learning and problem solving through advanced algorithms or with the help of machine learning to solve a problem and ultimately validate and verify the outcome. AI is an integral part of today's society and accompanies a user of a state-of-the-art mobile device daily. In its form of machine learning, AI has achieved tremendous success in image and video processing and recognition or natural language processing, to name a few examples. Apple's Siri, designed as the first digital personal assistant for a mobile device, uses language processing based on machine learning and it already celebrated its 11th birthday in October 2022. There are many more examples, and the sky appears to be the limit, as with every new and exciting technology. Now, with AI and machine learning becoming mainstream, the wireless industry discovered the potential of this, in quotes, old technology. So it's time to look at how our industry plans to eventually adopt this approach to improve the performance of cellular networks even further, what the potential challenges are, and how that all relates to our current approach of testing mobile devices and wireless networks. Today, we take a first step in this direction by discussing machine learning fundamentals. Let us start with reviewing some terminology. For example, from a Rohde Schwarz point of view, artificial intelligence is part of data analytics. By definition, we live in the age of narrow AI, or also called weak AI, which is defined by 5 key features. Logical reasoning, like for instance the chess champion AlphaGo. Perception, which I mean is image and face recognition, for example. Knowledge representation. An example is here IBM's Watson, trained for oncology. Language processing, I already mentioned Apple Siri, but there's Amazon Alexa and many, many more. And of course the entire field of planning and navigation, for instance the idea of having autonomous driving, self-driving cars. If there's weak AI, there's also strong AI, which means the machine intellectual capabilities are equal to or even superior to human-like intelligence. Of course, famous examples are intelligent robots or androids, like Data from Star Trek The Next Generation, Skynet in the Terminator movie series, or Hades in my favorite video game Horizon Zero Dawn. Machine learning is a subset of AI, which defines the ability to perform tasks without explicit instructions by relying on patterns. Or in other words, building systems that can learn from datasets instead from explicitly programmed instructions. Deep learning is one approach to machine learning. The learning process is based on artificial multi-layer neural networks using a large amount of data trained to retrieve patterns typically used for prediction or classification. And generally speaking, there's an overlap between data science, big data, and data management. If you talk about these terms and the related processing, you also talk about the cloud and cloud technologies. As mentioned, machine learning is a subcategory of AI. In very broad terms, machine learning algorithms build a model based on experience, also known as the training data. So it is a data analysis method that automates analytic model building. There are 3 types of machine learning algorithms defined based on the feedback available to the learning system. What do I mean by that? The first type is supervised learning, which is a task-driven and therefore similar to how humans typically learn. We identify a problem, apply our current knowledge, and solve the problem. If the answer is wrong, we modify our present knowledge and see if that solves the problem. In machine learning, the problem solution corresponds to the training data. The to-be developed model corresponds to the applied knowledge. Supervised learning requires labeled data as input and known or expected output as training data. The network now learns a rule to map the inputs to the desired outputs. Supervised learning is the method that found the most adaptation in the industry. See the examples that naturally everyone can associate himself with. The basis for this is 2 main subcategories. Classification means finding the classes the data belongs to. For example, classifying the face, image to one registered user. Regression. In contrast, regression does not determine the class the input data belongs to. Instead, it provides a value. A typical example for a regression problem is to have a dataset of age and income and to find a model that estimates revenue by age. The difference between classification and regression is the type of correct outputs. Classification requires classes, regression requires values. The next type is reinforcement learning, which uses input, some output, and the grade of the output as training data. A prominent example is the AI in a computer or video game, where it's reacting to the user's actions. In other words, the algorithm learns to respond to a particular environment. And last not least, unsupervised learning, which is ultimately totally data-driven, as it only uses unlabeled input as training data. It seems at first difficult to understand, but it eventually makes sense as this method is typically used to pre-process data, explore patterns, and predict the output, such as a customer segmentation or targeted marketing. Machine learning uses the concept of neural networks. Although some audience members have heard the term neural network and have a specific idea, I would like to discuss the fundamentals quickly so everyone has a general understanding. With neural networks, we try to model how the human brain operates. In straightforward terms, the brain consists of biological neurons, shown here, interconnected brain cells, which process and pass on chemical and electrical signals. Today, we know that such a neuron receives the input via the dendrites, passing the data to the nucleus of the cell body, which processes the information. Then they are passed onto the axon, a conducting fiber that connects to the transmitter, called the axon terminals. Finally, those axons terminals connect to the next neuron's dendrites. Intending to solve complex and multidimensional problems, the idea arose in computer science to model this behavior in software. The dendrites are our input values, x1 to xn, where we multiply the input values with a certain weights, sum them up, and add a bias. We pass the results on to an activation function that decides if the neuron fires or not. In other words, if it contributes to the output. One more word about the activation function. It yields the output or simply defines the perceptron's behavior. Today, there are several activation functions in use, initially sigmoid, to convert the input to an output that ranges between 0 and 1. This could be also achieved with tangent hyperbolicus, but most modern neural network uses either a softmax function or more recently a rectified linear unit function, which for example removes negative values from a dataset. As training my algorithm sounds very abstract to a computer scientist, the basic definition of training a neural network means to find and adjusting the weights and the bias. This is the concept of an artificial neuron, and I guess now it's clear that an artificial neural network is a combination of multiple artificial neurons. So let's put this into context from a test and measurement perspective. How about finding the settings on an instrument, like a signal generator and a spectrum analyzer, to measure the best error vector magnitude for any given signal? This is a typical method for customers to determine the performance of test equipment by measuring baseline EVM performance, connecting the signal generator directly to the spectrum analyzer, and recording EVM values while doing a power sweep from, say, minus 50 dBm to plus 10 dBm. If we plot those results, they typically form a bathtub curve. For lower power values, the system is usually noise limited. For higher power values, the system is driven into compression. Customers look for flat curves with the best EVM across a wide range of power levels. As one can imagine, there are quite some settings to consider to achieve the best EVM performance at a given power level. So back to machine learning. We could now think about a neural network that takes input parameters such as power level, the peak to average power ratio, the bandwidth, and the frequency of the signal. That are parameters that contribute, of course, to the best EVM performance. As output parameters, we want the reference level and attenuation setting that we need to apply to our signal analyzer. Maybe there's even a way to play with settings such as automatic gain control and other parameters that would tune the RF frontend of the signal analyzer to the desired settings. All we need now is training data, for instance, different kinds of 5G signals with different parameter combinations. As we all know, 5G is very flexible in terms of used numerology, bandwidth options, and modulation schemes. On top of that, there are numerous configurations of reference signals for different purposes, leading to minor or more considerable variations, for example, in terms of the peak to average power ratio of the waveform. Test equipment can help generate these data sets and use them for training a model to predict the best settings for the signal generator and spectrum analyzer. In addition, new and eventually unknown waveforms, ultimately standardized for 6G, would serve as a validation data to test the model's accuracy. So I just gave an example where machine learning might provide an advantage due to the complexity and multidimensional nature of the problem at hand. However, you can approach this deterministically and write software algorithms to adjust and fine-tune every setting. And this functionality is already today available for Rohde & Schwarz spectrum analyzers and signal generators. It is not based on a machine learning approach and leads to the same results, means the best settings for the particular waveform at the frequency and power level. There's no need to reinvent the wheel, and doing machine learning for the sake of machine learning makes no sense. As you can see, it is essential to identify the use case and fully understand the requirements to determine if machine learning provides a real benefit. Our industry has done so, and the first efforts are underway for 3GPP's 5G new radio standard to enable the usage of artificial intelligence and machine learning, not just for network automation and network management, but also for other areas, such as the air interface. This can be seen as a stepping stone on how AI and ML is used in a 6G standard. But what these identified initial use cases are is a topic for another video in our video series called Think 6, where we discuss interesting aspects for the next generation of wireless communication, aka 6G. Welcome to another video in our video series called Think 6, where we discuss exciting aspects of the next generation of wireless communication, aka 6G. In our last video, we explored the use of artificial intelligence and machine learning in wireless communication and learned some basics and fundamentals. Today, we want to explore some initial use cases currently studied by the 3GPP standardization organization as part of the next release for technical specifications for the 5G new radio standard. So welcome to part 2 of our mini-series on artificial intelligence, machine learning in future wireless communication. Last time we concluded that it is essential to understand use cases and requirements to determine if the use of machine learning provides a real benefit. With all the hype around artificial intelligence and machine learning, it is important to ask, what role will machine learning really play in wireless communication? It's the ultimate question of life, the universe, and everything, if you allow me to refer to the Hitchhiker's Guide of the Galaxy. And the answer is not 42, by the way. I like to compare the things that are going on with machine learning in wireless communication with the actual fusion process that powers our sun. During nuclear fusion, two hydrogen isotopes, deuterium and tritium, collide at super high speeds to fuse to a much heavier nucleus, that is, helium, release a huge amount of energy and one neutron. If we use this analogy, we can replace deuterium and tritium with 5G and machine learning, which fuse to 6G and release some innovation compared to the previous technology. And that innovation may be a revolution of the physical layer, where the complex, very sophisticated, but deterministic algorithms for detection, synchronization, channel estimation, channel equalization, and demapping are eventually replaced by machine learning models. But let's not get ahead of ourselves. Let's take a look on what's happening right now for 5G in terms of machine learning. That machine learning models replace blocks in the signal processing chain is and can't be the first step. First, a common understanding and agreement between industry players need to be established, as well as a framework that allows the evaluation, analysis, and comparison of results of simulations. This is what is going on right now within 3GPP. The standardization organization's RAN1 working group, in charge of the physical layer definition, agreed to answer these questions and all surrounding questions by exploring 3 use cases over the course of the ongoing work in 3GPP's Release 18. There are 2 study items in Release 18. The first one is artificial intelligence and machine learning for the 5G new radio interface. And a second study item on Artificial Intelligence and Machine Learning for the Next Generation RAN. Both study items shall build upon the results from the Release 17 RAN-free Let's Study item on data collection for NR and ENDC. According to our standards delegates, this study item that will transition into a work item for Release 19, the members of 3GPP allocated the largest time budget in the long history of 3GPP. This just marks the importance of this topic, also from a standardization point of view. The official timeline for 3GPP Release 18 foresees the syntax freeze by March 2024, which implies a freeze of the core specification in December 2023. That is roughly a year from now. And as a side note, Release 18 marks also the point where we call everything now 5G advanced. And as you can see, there are many more features and functionalities being worked on than just artificial intelligence and machine learning. For the air interface study item, the 3GPP members agreed on the following 3 use cases as a basis for their study. CSI-feedback enhancements, with the goal of an overhead reduction, improved accuracy, and channel prediction. Second, beam management, beam prediction in time and/or the spatial domain, overhead and latency reduction, beam selection accuracy improvement. And last not least, positioning accuracy enhancements for different scenarios, including those with heavy non-line of sight conditions. So let us discuss one of these use cases in more detail. Folks that are familiar with the 5G new radio know that the UE estimates the downlink channel quality based on so-called channel state information reference signals, short CSIRS. The UE executes channel estimation measurements on those reference signals, such as reference signal receive power, RSRP, reference signal receive quality, RSRQ, and reference signal interference to noise ratio. The estimated SINR, which is based on hardware and underlying software algorithms, is translated to channel quality indicator, CQI. At the same time, the device determines if it can perform MIMO operation or not, and reports the results as rank indicator, layer indicator, pre-coding type indicator, and pre-coding matrix indicator back to the network. The channel feedback is sent in form of a bit stream in uplink direction with the data channel if there's an uplink transmission ongoing, otherwise via the control channel. Of course, this is only a very high-level description. There are many, many details as the CSIRS can be very flexible configured, as you can tell from the ASN1 information elements that I copied here. Yes, it is an eye chart, and the idea is not that you read it, but more to show you the flexibility of how to configure these signals and allocate the required resources. The underlying configuration depends on a number of factors, including the hardware capabilities of the infrastructure, and that of course is vendor specific. The physical layer specification foresees several configurations depending on the number of antenna ports used and allows different mapping of CSIRS to this time frequency grid. As a result, this leads to varying number of feedback bits depending on the configured CSIRS resources, the reporting modes, and so forth. But most importantly, of course, the conditions on the radio channel and if there are many dominant vectors. The table here, copied from an actual paper published by Samsung, shows and compares the amount of feedback bits based on certain configurations and different 3GPP releases. We can see that this ranges from 351 bits to 58 bits. The second part of the table shows the number of bits required to transmit the same information after being compressed by an autoencoder, which is an unsupervised artificial neural network that learns how to efficiently compress and code data and then learns how to reconstruct the data back from the reduced encoded representation to a representation that is as close to the original input as possible. Let's take a look at the high-level principle. So the original idea to compress feedback for channel state information was already explored by several universities and research institutes in China as part of a challenge. A summary of this contest is given in the paper from June 2021, where you find the title and the link at the bottom of this slide. The problem description aligns with the discussion we had a few seconds ago. It is argued that only limited channel feedback is provided based on an extraction from the complete channel state information. However, providing full channel state feedback is an implementation challenge due to the difficulty of developing adequate compression and recovery mechanisms based on using the traditional approaches. What do I mean by that? Well, think about the scenario shown here, top left. There's a transmitter and a receiver, multipath propagation on the radio channel where the signal arrives via different paths at the receiver. The term cluster has slightly different definition in 5G new radio than just describing a path, but let's leave that out here for simplicity for the moment. The channel metric H is now described by the channel coefficients from the nth transmit antenna, the nth receive antenna, and the dth cluster. So in the paper, the provided data set corresponding to the channel matrix at a given time has 24 paths and 16 antenna pairs due to 4 transmit and 4 receive antennas. We have then to deal with the real and imaginary parts and code each sample with 32 bits. That means the full channel state feedback corresponds to a total of 24,576 bits. That's many bits to be transmitted just to provide full channel state information. This is why 3GPP spends so much efforts coming up with techniques and procedures to reduce this overhead. For the mentioned challenge to solve this problem by using machine learning techniques, more than 900 teams registered. The goal of the challenge was to develop an autoencoder that compresses the data so that the receiver can recover the information with a normalized mean square error of less or equal to 10%. This table summarizes the overall results. The winning team came up with a machine learning model that compresses the data by a factor of almost 86. That is a fantastic result, and as now 3GPP is looking into this topic as well, this approach eventually becomes reality. With that, we have reached the end of our second video in our mini-series where we explore the role of artificial intelligence and machine learning in wireless communication, and took a look at the initial use cases analyzed by 3GPP as part of a Release 18 study item. Next is to see how a future 6G standard will build upon these definitions and findings. However, this is a topic for another video in our video series called Think 6, where we discuss interesting aspects of the next generation of wireless communication, aka 6G. Welcome to another video in our video series called Think 6, where we discuss interesting aspects of the next generation of wireless communication, aka 6G. In our last two videos, we learned the basics of machine learning and looked at one of the 3 use cases that are currently explored by 3GPP as a study item for Release 18. Today, we look even further into the future by exploring how this initial work may transform the air interface and in particular the physical layer for a future 6G standard. So welcome to part 3 in our mini-series on artificial intelligence and machine learning in future wireless communication, where we will take a first look on how an AI-native air interface for 6G might be realized. So the question is, what may change with 6G? Here you see a simplified block diagram of the common signal processing chain for the transmitter and the receiver, including the RF front end and antenna system. The characteristic of the wireless channel impacts the transmission and challenges the receiver to recover the signal correctly. In the past years, you find that academia and even key industry players began to explore replacing individual blocks in this chain with machine learning-based models. The next step is to combine blocks that logically belong together. For example, design and train a neural network that can perform channel estimation, equalization, and demapping. We would call that a neural receiver. The next massive step is to use machine learning to jointly optimize the entire chain for transmission, reception, and baseband processing. The ultimate goal of machine learning is to adapt the transmission to the environment which means the underlying hardware, signal processing techniques, and application type. That implies that machine learning designs part of the physical layer itself. So, for example, the resulting waveform and constellation that cope with the channel characteristic, analog impairments induced by the transmitter and receiver components, and signal processing errors coming from the baseband processing. Those constellations may look much different from today's constellation diagrams of a QPSK or any of the QAM modulation. To do this end-to-end learning of a communication link, the concept of an autoencoder comes into play again. All of the above should trigger the question of when is all of this happening, and does it happen at all? Of course, it's hard to predict the future, and there's no chance to give any dates here, but from our analysis and current understanding, this may occur in 3 phases. Phase 1 focuses on the RF frontend. Phase 2 focuses on the receiver aspects, and Phase 3 for an end-to-end optimization, but given the associated challenges, has a big question mark at the moment. Let us discuss these phases a bit more in detail. We see Phase 1 as very likely to happen. First papers on this subject using machine learning to model the nonlinearities of the transmitter came out in 2020. Initially driven by universities, key industry players also published their findings towards the end of the year, suggesting that machine learning can outperform the classical methods to find, for example, digital pre-distortion models to linearize the power amplifier. The next step is to apply the concept to the entire frontend, data sets to train the neural network. And I mean a lot of data. This data is not always easily accessible or even available to everyone who wants it. It provides one of the challenges for machine learning, particularly for wireless communication. So to understand why Phase 2 may happen, we need first to know why there's room to apply machine learning for signal processing at the receiver side. If you are familiar with the 5G new radio standard, you know there's a zoo of reference signals designed to serve different purposes. The diagram spans the resource grid in time and frequency for a single resource block with 12 subcarriers on the y-axis and 14 OFDM symbols on the x-axis. The orange-marked resource elements carry the demodulation reference signal sequence for the data channel. The receiver uses these pilot signals to perform least mean square channel estimation, equalizing all resource elements closest to the next pilot. For example, the information gained from the bottom left pilot signal in symbol number 2, subcarrier number 0, is used to equalize all resource elements within the purple rectangle. If we look at one area in more detail, we can conclude that the equalization process for the resource element closest to the pilot works pretty well. However, moving away from the pilot signal leads to equalization errors due to channel aging and imperfect channel estimation based on the deterministic compute algorithms. Various scientific papers demonstrate that machine learning can overcome these equalization errors and improve this mismatch. So the theoretical performance gains are quite significant. Here's an example from Nokia Bell Labs' work presented at the Artificial Intelligence Machine Learning for 5G Challenge organized by the International Telecommunication Union back in November 2020. If we compare the baseline, that's the pink curve, with the perfect channel knowledge curve, which is the orange one, and target a block error rate of 1%, we can estimate that there's a room for improvement of a little over 3 dB. Now with the neural receiver represented here by the blue curve, based on a fully conventional neural network that replaces channel estimation, equalization, and demapping, we get very close to the perfect channel knowledge performance. So that shows that machine learning can outperform the traditional signal processing in this case because it applies a data-aided channel estimation, equalization, and demapping. But what is the ultimate step that researchers envision? It is to learn the communication link from an end-to-end perspective using, for example, an autoencoder approach. A potential result looks like this. It's coming from the same presentation. A trained constellation for specific channel profiles and Doppler spreads. The constellation looks way different than the traditional QAM modulations. It's not symmetric at all, which is required so that the receiver can synchronize to this adapted waveform. The additional performance gain comes from the fact that this learned constellation does not need any pilot or reference signals anymore. The freed up resource elements can now be used for data transmission and therefore contribute to another performance gain. With that, we have reached the end of our third video in our mini-series where we explore the role of artificial intelligence and machine learning in wireless communication, and we took a look on how an AI-native air interface for 6G may look like. Next is to evaluate what the potential impact on test and measurement solutions is. However, this is a topic for another video in our video series called Think 6, where we discuss interesting aspects of the next generation of wireless communication, aka 6G.
Hello, and welcome to the fourth episode on the topic of artificial intelligence in wireless communication in our Think 6 video series. With the advancements in artificial intelligence in its form of machine learning, many researchers and key industry players believe that a future 6G standard will natively support AI and ML for the air interface. After introducing the basic concepts and some use cases in the previous videos, today it's time to see AI in action. We will have a look at the live demonstration to observe the potential of machine learning in the physical layer. We are very excited that we partnered up with a team of researchers at NVIDIA to build a testbed to verify the performance of a neural receiver in a real-world hardware-in-the-loop setup. I'm glad that Sebastian Kammerer from NVIDIA is joining us today here. Sebastian, you have been working on neural receivers for quite some time now. Could you introduce the concept to our viewers?
Sure. So welcome also from my side. It's great to be here and to give you some inspiration from NVIDIA's research perspective of how future wireless receiver algorithms could be designed. Today, we will look into a research prototype that replaces significant parts of the classical physical layer algorithm by trainable neural networks. So in particular, we will replace channel estimation, equalization, and demapping by a single neural network. So let's have a look at the classical system first, where the task is to reliably communicate between a transmitter and receiver over a noisy channel. In traditional signal processing, we have the transport block encoding, modulation, and OFDM mapping, and at the receiver side, we usually do the somehow inverse operations of these encoding blocks. Now, the idea, or the core idea of a neural receiver is to replace the channel estimation, the equalization, and the demapping by a joint neural network that jointly learns to perform these tasks in a single signal processing step. Let's have a detailed look at what we will show in this demo. So the scenario is a 5GNR compliant multi-user MIMO setup. For the demo, we have 2 users each equipped with 2 transmit antennas, and the receiver has 4 receive antennas. The architecture itself is flexible, can be easily adapted to different setups. In many cases, this works without retraining. We work with 5GNR compliant signals, in this case for the push, so we work in the uplink direction, and 80 MHz bandwidth.
Great, thank you, Sebastian. This is quite an advanced scenario. Researchers performed lots of investigations on neural receivers and simulations in the past. We are very excited that our Rohde & Schwarz test and measurement instruments bring the development and verification of neural receivers to the next level. For the first time, we validate the functionality and the performance of a neural receiver with a fully 5G compliant RF signal in a hardware-in-the-loop test setup. Let's have a brief look at the testbed setup. All the way on the left side, you see our signal generator, which generates the MIMO signals for the 2 users that are then captured by a signal receiver. The signal receiver down-converts the data and streams it out to our 5G uplink measurement system, which performs time synchronization and FFT calculation. Afterwards, the resulting data is streamed to the server by NVIDIA, which is equipped with a GPU and executes the neural receiver. Here you see our Rohde & Schwarz SMW200A vector signal generator and 2 SGT100As that allow us to generate the 4 MIMO 5G signals. You can see here on the screen that we configured the 2 users and that each user is faded individually and that noise is being added individually as well. We are operating at a carrier frequency of around 2.1 GHz, although this is configurable. The transmitted signals are captured by our Rohde and Schwarz MSR4 multipurpose satellite receiver and down converted. We stream the IQ samples to our Rohde and Schwarz server-based testing signal analysis system via 10 gigabit Ethernet and afterwards to the NVIDIA GPU. Those two devices are not visible here in our setup. All right, enough introduction. Let's have a look at the live demo. What you can see here are simulated transport block error rate curves. Sebastian, can you explain the curves a bit before we start the measurement?
We can see 4 curves, which are all evaluated for the same scenario and the same input data, but for different receiver implementations. The gray curve shows the block error rate on a transport block level, including the entire physical layer effects, versus the SNR for a perfectly known channel at the receiver. This is obviously not realistic, but gives a lower bound of what a perfect system could possibly achieve. The blue curve shows the performance for least square channel estimation, which has a fairly low complexity and can be considered as a practical baseline. The orange curve shows an approximation of maximum likelihood that achieves a great performance, but is not practical due to its very high computational complexity. And finally, the green curve shows now the performance of the neural receiver after training. As can be seen, it performs close to the maximum likelihood performance, but with a much lower computational complexity.
Okay, so in this demo, we will now verify the performance of the neural receiver with the Rohde and Schwarz test and measurement instruments in the testbed that we just introduced. Clicking the button here above the curves, start the operation of the entire testbed. We're sweeping over the SNR range, starting at minus 1 dB, and increment the SNR configured in our signal generator by 1 dB with each measurement. The blue dots that are now starting to appear show the measurement results, so the transport block error rate that is determined at the neural receiver output. It takes a little while for the entire measurement to complete, so let me give you some background on the training in the meantime. The model has been trained on a very diverse urban microchannel model as specified by the 3GPP with random user speeds and also random user locations. For the evaluation, we then chose individual channel models for each of the 2 users. For the first user, we selected the TDL-B model with the 100 nanosecond delay spread and a Doppler frequency of 400 Hz. For the second user, the TDL-C model with a 300 nanosecond delay spread and a Doppler frequency of 100 Hz. We could also pick different channel models as long as the characteristics are included in the training dataset. As more and more blue dots appear now, we can see that the measured block error rates are very close to the ones obtained in simulations. So it's great to see that we are able to reproduce the simulation results in our real-world testbed setup using the fully 5G compliant RF signals generated and received by the Rohde and Schwarz test and measurement instruments. So Sebastian, let's talk a bit about the technical details. Can you give us an overview of how the neural receiver was trained?
Sure. So for the training, we have developed Shona, which is NVIDIA's GPU accelerated link level library for the physical layer. So it's an AI native library, so we can have machine learning and machine learning tools already built in. And it also supports the generation of 5G compliant signals, such as in this case, the push signal. And that helps us to generate the synthetic data set that we use for training. And in particular for this neural receiver, the problem is that these neural receivers tend to overfit, which means actually if we would have just trained it for the specific channel model that we are using here, we would overfit to the specific setup. But what we actually want in practice is we want a receiver that works for a wide set of different channel realizations. And for that, we use these built-in channel models in Shona and sample different user speeds, different delay spreads, and different Doppler spreads, for instance, Doppler shifts. And the idea is to get a very rich data set of different channel realizations and to get a very universal receiver after the training. So the training itself roughly takes 2 to 3 days here, depending on the performance that you want to achieve.
Okay, great. We talked about complexity a bit already. What performance do we see here?
So at the moment, we are at roughly 50 slots per second, which is an equivalent of 7 to 8 megabit per second in terms of throughput, information rate throughput. But you have to see that Shona is for fast prototyping and to have research prototypes and kind of realize your ideas fast, but it's not made for real-time implementation. So the next step would go towards low-level implementations of such a concept.
Okay, final question. How can you imagine this being applied in 6G?
So beyond pure block error rate or bit error rate and performance improvement, of course, our long-term vision is to have a site-specific base station that can actually learn to improve the performance even after deployment. So think about a base station that is deployed close to the highway, where we have a high user mobility, or another base station that is actually deployed in some indoor factory environment where the mobility is rather low. Or think about different delay spreads depending on the environment where the base station is actually deployed. And we think that these neural receivers could be one technology or one enabler that enables such a site-specific base station that could be even retrained after deployment and could continuously improve the performance during the lifetime of such a base station. So this is one vision we have for 6G and one area of research where we actively work on, and we hope that there will be a lot of new insights and breakthroughs in the next years to come.
Great. Thanks for the insights, Sebastian. We are very excited that together with NVIDIA, we can transfer the concept of a neural receiver from theory to practice using our Rohde and Schwarz test and measurement instruments. With such a test bed in place, we are now able to take the next steps and support research in addressing key concerns such as complexity, power consumption, and also the throughput of neural receiver implementations. Even though research is still in an early stage and there is still lots of work that needs to be done, we are very excited to show the potential of AI in the physical layer that may become a part of 6G communication systems.
예, 지금까지 저희가 준비한 저희 로데슈바르즈 본사에서 준비했던 영상이었었죠. 중간에서도 계속 언급이 되었습니다만 싱크6 시리즈의 동영상으로 저희가 선정한 내용들을 가지고 머신러닝과 AI에 관련된 내용, 그리고 6G의 이러한 내용들이 어떻게 반영될 수 있느냐, 뭐 이런 내용들을 쭉 함께 보셨습니다. 뭐 결론적으로 생각을 해보자면 일단 제가 생각하기에는 그건 것 같아요. 이제 5G나 6G나 이런 통신 기술에서 AI와 머신러닝과 같은 기법들을 도입함으로써 이 실질적인 그 RF 환경에서의 어떤 그 네트워크 최적화, 망 최적화 같은 부분을 계속 실시간으로 계속 적응형으로 만들어질 수 있는 이런 부분들이 우리가 6G 통신에서 생각할 수 있는 어떤 AI의 적용 내용이 아닐까, 뭐 이런 생각이 들고요. 이런 걸 통해서 각각의 사용자들이 더욱더 최적화된 어떤 데이터 전송 속도 혹은 체감할 수 있는 어떤 성능 향상, 뭐 예를 들자면은 뭐 우리가 흔히 이야기하는 그 특화망이 있죠. 5G 특화망, 이음이라고 보통 표현하고 있는데요. 이런 어떤 프라이빗 네트워크에서 좀 더 안정적인 이런 내용들을 구현할 수 있도록 어떤 그 성능 개선이라고 해야 될 것 같습니다. 이런 부분들을 만들어주는 어떤 그 툴, 이런 개념으로 생각해 볼 수 있지 않을까, 이렇게 생각이 됩니다. 이 부분은 뭐 제가 처음 생각했던 뭐 서두에서도 말씀드렸습니다만은 챗GPT처럼 생각할 수 있는 부분은 아닐 것 같고요. 이런 부분들이 이제 실제로 어떤 기법으로서 어떻게 나타나지를 또 릴리즈 19라든지 이런 어떤 그 실제 규격에서 반영되는 내용들을 또 추후에 우리가 재미있게 기다려볼 수 있지 않을까, 이런 생각이 듭니다. 유승근 매니저님, 오늘 지금
네.
질문이 엄청 많이 올라왔어요. 이제 아무래도 이게 6G라고 하는 토픽이다 보니까 지금 관심 가지고 계시는 분들이 굉장히 많은 것 같습니다. 이게 시간이 지금 한 5분 정도 남았을 것 같은데 6분 조금 안 되겠네요.
네.
뭐 답변해 주실 수 있는 부분들이 있다면 좀 어떻게 답변을 좀 해주셨으면 좋겠습니다.
네, 알겠습니다. 우선 가장 먼저 질문 주신 장혁수님께서 스토리지에 관한 고민, 그리고 성능 비용 경계선에서 고민한다고 말씀을 해주셨는데, 저희는 이제 스토리지 업체는 아니기 때문에 그 차별화된 솔루션 관점이라기보다는 이 AML 말씀하신 것처럼 AI ML을 하시면서 이제 고성능 스토리지나 이제 병목 현상들이 말씀하신 것처럼 발생을 할 수가 있습니다. 그래서 업계에서는 지금 AI 칩셋으로 반도체로 GPU, 그래픽 프로세싱 유닛을 사용하고 있는데, 이런 부분들을 이 연산 처리 속도나 그리고 전력 소모량에 좀 영향을 미칠 수가 있어가지고 이 AI 전용 칩셋들, 뭐 예를 들면 뉴럴 프로세싱 유닛, 이런 것들을 개발하려고 노력하고 있고요. 그리고 또한 말씀하신 것처럼 속도적인 측면에서 이 속도를 빨리 데이터를 수집하고 전달하고 주고받아야 되기 때문에 이 속도 쪽을 개선할 수 있는 PCI 6.0, 7.0에서 예를 들면 100기가 100기가 bps 속도를 처리할 수 있는 이런 스탠다드들이 출시가 되고 있습니다. 그래서 이런 스탠다드들이 출시되면서 문제가 발생하는 것들이 데이터를 이제 스토리지 하는 부분도 문제인데 얘들 주고받으면서 이 고속인 속도 때문에 서로한테 영향을 미칠 수 있습니다. 크로스톡 문제가 생기는 부분이 있는데 이런 부분들은 저희 계측업체인 네트워크 아날라이저를 통해서 이제 측정할 수 있는 솔루션들이 개발되고 있고요. 이런 부분들은 저희가 아마 올해 4월이나 5월쯤 또 다른 웨비나를 통해서 좀 더 자세한 내용들을 말씀을 드릴 수 있을 것 같아요. 그래서 저희 계측업체 같은 경우는 아까 보신 것 같이 뉴럴 리시버를 개발하는데 사용할 수 있는 소스원이나 페이딩이나 그 노이즈 성분들을 만들어내는 부분과 그리고 그쪽에 사용되는 하이스피드 인터페이스에 대한 솔루션을 제공하고 있다고 보시면 될 것 같습니다.
지금 말씀하신 솔루션이 아마 제 생각으로는 대표적으로 말씀하셨던 이제 네트워크 아날라이저라든지
맞습니다.
이런 부분 혹은 뭐 고성능 오실로스코프 이런 부분들이 될 것 같아요.
네. 그런데 오실로스코프에서 이제 접근하기가 좀 힘들어진 게 얘네들이 이제 하이스피드다 보니까 주파수 자체를 측정해야 되는 게 30기가, 50기가 이렇다 보니까 오실로스코프 뭐 100기가 솔루션까지 있지만 레졸루션 관점에서 조금 문제가 있어서 그렇게 접근하는 것보다는 그것보다는 이제 크로스톡 서로한테 영향을 미치는 그런 부분에 대해서는 오실로스코프보다 네트워크 아날라이저 관점에서 접근하는 게 더 맞기 때문에 네트워크 솔루션으로 몇몇 큰 업체에서 지금 이미 접근을 하고 있습니다. PCI 6.0 그리고 이더넷 IEEE 802.3 스탠다드에서 만든 그런 것들을 테스트하기 위해서 이미 접근하고 있는 부분이라고 보시면 될 것 같습니다. 그리고 또 다른 질문이 있었는데 두 번째 이제 질문 올려주신 이용진님께서 AI ML은 6G와 관계없이 개별적으로 개발될 수 있지 않느냐고 질문하셨는데 맞습니다. 개별적으로 할 수 있는데 저희가 여기서 언급하는 대부분의 6G의 AI ML은 3GPP라는 단체 4G, 5G를 만든 단체에서 어떻게 이걸 이동통신에 접목을 할지에 대해서 얘기가 되고 있는 부분이어서 챗GPT랑은 이제 별개로 연계될 수 있지만 3GPP에서 이 이동통신을 어떻게 이끌고 가는지는 다르게 보실 수 있으실 것 같습니다.
지금 이 3GPP 스펙이 제가 알기로는 지금 현재 가장 마지막 버전이 릴리즈 17이었던 것 같아요.
릴리즈 18까지 완성이 됐습니다.
18까지 완성됐나요?
네.
그럼 릴리즈 18에서 지금 저런 AI나 ML과 같은 부분들을 규정을 하고 있습니까?
네, 맞습니다. 그래서 아직 상당히 초창기인 단계지만 동영상 이제 두 번째에서 언급된 것처럼 CSI 피드백이랑 빔 매니지먼트, 포지셔닝 엔하ን스먼트 등이 있었는데 이걸 릴리즈 18에서 연구가 다 끝나지 못해서 릴리즈 19로 다 옮겨져서 계속적으로 연구를 이어갈 예정이고요. 그리고 거기에 이제 추가적으로 다른 AML 기술들이 있는지는 저희도 체크를 하고 있는 중이라고 보시면 될 것 같아요. 그래서 현재는 이 이제 3GPP와 이제 별개로 이제 움직이는 부분이 저희 이제 동영상 네 번째 보여드린 것처럼 뉴럴 리시버에 좀 더 포커스를 맞춰서 개발되고 있다고 보시면 될 것 같습니다. 그리고 시간상 이제 한 개 더 질문을 받을 수 있을 것 같은데요. 조금 관계된 걸 좀 찾아보면은 어떤 게 좋을까요? 그리고 요거는 지금 AI/ML과는 임종택님께서 질문해 주신 부분이 있는데, 요거는 AI/ML과는 조금 거리가 있지만, 6G 통신을 위해서 위성통신과 연계한 통신체계가 지원돼야 된다고 하시는 부분이 있는데, 이러한 부분들은 또 동일합니다. 3GPP 자체에서 이 위성통신을 자기들 어플리케이션으로 가져오려고 하는 부분이 있습니다. 기존에는 그 세틀레이트를 쓰는 그런 것들은 자기만의 스탠다드를 가지고 있었는데, 이러한 부분들 이제 5G, 6G를 접목해서 기존에 있던 지상국과 이제 연동해서 이제 사용하시려는 부분이 있습니다.
지금 말씀하신 부분이 아마 5G NTN을 말씀하신 것 같습니다. 예, 그래서 이런 부분들은 또 저희 로데 슈바르즈에서 준비한 또 다른 웨비나들이 있었어요. 그리고 또 앞으로도 이제 계속 그 업데이트되는 내용에 맞춰서 저희가 또 어떤 내용들을 말씀을 드릴 수 있지 않을까 하는 생각이 들어가지고요. 이런 부분들은 또 흥미롭게 또 지켜보시면서 저희가 준비하는 내용에 맞춰서 또 생각을 해봐 주시면 또 재밌는 결과가 나오지 않을까라고 생각을 합니다. 예, 유승근 매니저님 아까 말씀하신 것처럼 지금 시간 관계상 지금 저희가 3시까지로 지금 예정을 했었는데 지금 시간이 거의 다 됐습니다. 그래서 아마 오늘 지금 굉장히 많은 질문들을 올려주셨어요. 그래서 6G나 AI, ML 뿐만이 아니고 이제 6G 전반 그리고 이제 5G 혹은 5G 비욘드 뭐 이런 부분들까지 포함을 해서 굉장히 다양한 내용들을 올려주셨는데 죄송한 말씀입니다만 저희가 시간 관계상 오늘 여기 현장에서 모든 내용들을 다 답변을 드릴 수는 없을 것 같고요. 그래서 저희 이 내용들은 저희가 별도로 여러분들께 개별적인 답변을 또 따로 드릴 수 있도록 준비를 하겠습니다. 저희가 올려주신 질문들을 개별적으로라도 꼭 답변을 드리고 있기 때문에 이런 부분들은 여러분께서 좀 양해를 좀 해주실 수 있는 부분이 아닐까 좀 부탁을 드리고요. 오늘 말씀드린 이 내용들은 저희가 웨비나 다시 보기를 저희 로데슈바르즈 코리아 홈페이지에서 또 제공을 합니다. 그래서 여러분들께서 혹시라도 추후에 이제 어떤 내용들을 다시 참조를 하신다거나 혹은 오늘 들으셨던 내용 중에서 또 다시 또 한번 확인하시고 싶으신 내용이 있으실 경우에는 또 저희 로데슈바르즈 코리아 홈페이지를 통해서 또 내용들을 보시면서 또 참조하시면 또 다시 어떤 리마인더 개념으로 사용하실 수 있지 않을까 또 이런 생각이 듭니다. 6G 2030년 상용화를 목표로 움직이고 있기 때문에 아직은 시간이 좀 한 5, 6년 정도 남지 않았나라고 생각을 합니다. 그런데 또 사실 반대로 생각을 해보면 5G도 또 생각보다 금방 또 다가왔던 것 같아요. 그리고 그 과정에서 얼마나 만족했느냐 이런 얘기들은 차치하고서라도 일단 기술적인 어떤 진보나 이런 부분들은 생각보다 빠르게 흘러가는 부분들이 또 있는 것 같아 보여서 이 6G에 대한 부분도 또 계속적으로 우리가 좀 주목해야 할 그런 분야가 아닐까라고 생각을 합니다. 저희는 말씀드렸던 것처럼 또 여러 가지 내용들로 또 준비를 계속 하면서 또 아까 동영상에서도 보셨습니다만은 저희 같이 함께 하시는 파트너사들과 또 함께 또 좋은 내용으로 또 준비를 해서 여러분들께 계속 또 내용들을 드릴 수 있도록 준비를 하겠습니다. 오늘 참석해 주신 참석자분들께 다시 한번 저희 감사 말씀을 다시 한번 드리고요. 저희는 오늘 준비한 내용을 이 정도로 정리를 하겠습니다. 또 다음번에 재미있는 내용들 또 흥미로운 주제로 또 웨비나를 마련해서 여러분께 찾아뵙도록 하겠습니다. 오늘 참석해주신 여러분들께 감사드리며 오늘 웨비나를 이 자리에서 마치도록 하겠습니다.
감사합니다.